and welcome to Electric Fields Lesson 1A. So, we're going to start today by talking about the forces between charges. So what does that mean? Well, it means, let's go back to this question. Why can't I push my finger through my hand? The answer is, talked about this before, it's because the electrons on the outside of my finger and the electrons on the outside of my hand repel each other. So there's a force there, and you can feel it. If you push into your hand, you can feel that force. That's why it hurts. Yeah? And the force between two charged particles is given by this equation. It is equal to 1 over 4 pi epsilon naught, and this bit's just a constant. Okay, so that's just a constant, so that's just to make the maths work. The magnitude of the first charge multiply the magnitude of the second charge divided by the distance between them, which is little r, same as in gravity, squared. So F equals 1 over 4 pi epsilon naught, Q1, Q2 over r squared. A couple of subtleties here. Firstly, nothing in this equation will tell you the direction of the force. Nothing will tell you if it's repulsive or attractive. It'll just tell you the magnitude of the force. But like all forces, they need a direction. And you can define that direction any way you want. And you should just know that like charges are going to repel and charges which are different to each other will attract. The next thing which is really neat is this little epsilon naught. Because electric fields have a little difference to them than gravitational fields. Gravitational fields spread out through the universe. They go on for ridiculously long distances, and nothing really changes that. There's nothing you can hold up to block the gravity. Yeah? If the moon suddenly got a lot closer and people were just being plucked up off the Earth and flying towards the moon as they were pulled towards the moon's gravity, which wouldn't happen because the Earth's heavier than the moon. The sun got much closer to the Earth, people being plucked up and fly towards the sun's gravity. There's nothing you can really hold up to sort of block the gravity waves. Gravity just sort of spreads out through the universe. But electricity isn't like that. Electricity changes massively depending on the medium through which it's propagating, which you probably noticed. Because like electricity in water, it's really, really exciting, whereas electricity in bricks, nothing really happens. So electric fields aren't like gravitational fields. Gravitational fields just sort of happen. But electric fields propagate differently through different materials. And epsilon naught is the propagation factor, through a vacuum. So this means that this is the force equation for two charges which are in a vacuum. Also, it turns out epsilon naught works perfectly well for air, because air and vacuum in this turn out to be the same. There's basically nothing there blocking electricity, so fine for both of them. But this epsilon naught only works if it's in air or a vacuum. If we are using a different media, we have to use a different value of epsilon. And you can have an epsilon for anything you want. You can have an epsilon for water, an epsilon for brick, or an epsilon for wires. It doesn't really matter. But crucially, you have to put in different factors, which you don't need to in gravitational fields, because they just sort of, they don't care. They just happen. You can't block the gravity waves, but there's lots of ways you can sort of block or mess with electric fields. Cool. So this is how we calculate the force between two charges. There's a couple more equations I just want to touch on quickly, which is electric field strength, which is given the symbol capital E, is defined a little bit differently to gravitational field strength. Gravitational field strength is defined as the force per unit mass, force per kilogram. This, unsurprisingly, is force per unit charge. What is unit charge? Can you remember? It's a coulomb, which I also want you to remember is a lot of charge. Each individual electron has 10 to the minus 19 coulombs on it, so you need loads and loads of electrons to get an entire coulomb of charge. So coulombs a lot. You're normally dealing in millicoulombs, microcoulombs, tiny, tiny fractions of a coulomb. But electric field strength is also equal to the potential, which remember we wrote as V, divided by the distance. Exactly the same as gravitational field strength. The closer together the field lines are, closer together the potential is, for a given distance, the higher the field strength. But there's a really neat trick we can do. Because these are both E, we put them equal to each other. So you can say F over Q is equal to V over D. We can rearrange and we can say force times distance, which you already know is a measurement of work done, is equal to the charge times the change in potential. So if you know what the force is and how long it is, when you're sort of doing the force distance equation, you can flip that into charge potential equations and vice versa, which turns out to be useful in all sorts of different areas of electric fields. Okay, there's a couple of questions underneath. See you in the next video.